Good morning, afternoon, evening everyone. Today, I'm here to discuss the two types of electrical current, alternating current, AC, and direct current, DC, and their respective applications, represented on a voltage, V, time, T, graph, with AC having a sine wave curve. Let us compare the differences between the two and analyze their various applications. Alternating current is a form of electricity that reverses its direction and its intensity over time. It is widely used to power many different kinds of machines, from small devices to large industrial machines. Its principal benefit is that it can span long distances with little loss in power. Alternating current, AC, is a type of current that periodically switches directions. The voltage and time graph for AC resembles a sinusoidal wave, with the voltage varying periodically between a positive maximum and a negative minimum. Electricity is distinguished by two forms: alternating current, AC, and direct current, DC. In AC, the flow of electric charge periodically reverses direction, while in DC the electric charge only flows in one direction. This contrast has an impact on many applications of electricity. The equations in this slide illustrate the alternating current pattern. The peak voltage is proportional to frequency, and the peak voltage is the greatest voltage and current present in a single wave. The angular frequency of the AC signal can be expressed using the formula omega t, omega being the angular frequency and t being time. This implies the time it takes to complete one full cycle is inversely related to the frequency of the AC signal. The representation of alternating current shows a source voltage that changes with time. It can be represented by the equation V equals epsilon sint omega t plus epsilon 0. This form of alternating current is utilized globally for various electrical applications. AC is a type of electric current that varies in magnitude and direction over time. It is generally shown as a sine wave with a peak value and frequency. These values allow us to compute the time period and angular frequency of the current. The instantaneous value of the current at any given time can also be used to understand the phase. No greetings or thanks necessary. I'm here to discuss the concept of alternating electromotive force, which is represented by the equation EMF equals EMF 0 sine omega times t. This equation describes an EMF whose magnitude changes with time and whose direction reverses periodically. EMF 0 in the equation refers to the peak EMF or the maximum EMF. Alternating current is abbreviated AC or AC, not AC or AC. Through this equation, we are able to understand the alternating nature of this type of current. Electricity is transmitted through power systems using alternating current. This form of current is favored due to its ability to be sent over large distances while kept at high voltage and low current. The advantages of this are both a reduction in line loss and lower costs and improved efficiency. Correct abbreviation of alternating current is AC. It is an electric current that reverses direction in a circuit, and it is different from direct current that flows in only one direction. AC is the preferred abbreviation to differentiate it from other potential abbreviations. Drawing attention to the instantaneous value of an alternating current, or its electromotive force, often abbreviated EMF, is an important part of electrical engineering. This value measures the peak current or voltage in a waveform, typically the top or bottom of the sine wave. Analysis of the time-varying part of a current or voltage in an electronic circuit is used to determine this value. Understanding this concept is crucial in order to design more efficient systems. The value of current or EMF at a particular instant is a crucial aspect of alternating current. This peak or maximum value of current or EMF is measured at any given time and is called the crest or amplitude value. Knowing the peak or crest value of current or EMF helps us to comprehend the electricity flow in AC circuits and its impact on various applications. The concept of mean or average value of alternating current or voltage is important in order to measure its amplitude and frequency. In a full cycle, the current is zero because it is positive in the first half cycle and negative in the second half cycle. The average value is calculated by taking the arithmetic average of all the instantaneous values in a sine wave over a half cycle. This value helps to accurately measure the amplitude and frequency of an alternating current. proof of the average value theorem of alternating current showcases its usefulness in analyzing AC circuits. By partitioning the function into individual components, we can work out the average value of power over a specific duration. This theorem is incredibly valuable as it enables us to ascertain the outcome of a circuit with greater accuracy. Understanding the mean or average value for half-cycle of alternating current is beneficial for electricity providers, enabling them to adjust the current to an optimal magnitude. Having this knowledge enables providers to guarantee a consistent supply of electricity to their customers. The root mean square or RMS value of current is the square root of the mean of squares of all the instantaneous values of current over one complete cycle. It is also called the effective value, or virtual value, of current. Similarly, for the alternating current, the root mean square or RMS value of the EMF is also the square root of the mean of squares of all the instantaneous values of EMF over one complete cycle. The root mean square value of current is an important measurement of the amplitude of an alternating current waveform. It is the same as the value of direct current that would generate the same amount of heat when passed through a given resistance. To find this value, the average of the current over an entire cycle of the waveform is taken. This equals the base amplitude multiplied by the sine of the angular frequency times t. Discussing alternating current, particularly the RMS value of AC, is the topic of today. It is known that the voltage of an AC source is its RMS voltage, and the current in an AC circuit is its RMS current. Furthermore, it is noteworthy to recognize that AC ammeters and voltmeters are both reading the RMS value, also referred to as the effective value of alternating current and voltage. Alternating current is a type of current which can be measured with hot wire ammeters and hot wire voltmeters, as the heat produced is independent of the direction of the current. Interestingly, the amount of heat produced is the same as the heat produced by direct current of the same magnitude, making alternating current an ideal choice for electric power distribution. AC, also known as alternating current, is a powerful current type that can be hazardous. DC, or direct current, is not as dangerous as AC as the same voltage of AC can be more lethal. As an example, 200 volts DC is equal to 200 volts AC. Thus, electricians need to take extra safety measures while dealing with AC due to its higher voltage. AC can be generated through the concept of electromagnetic induction and follows the principles of Ohm and Joule, implying that it includes resistance and produces heat as it moves. The average EMF during the positive half cycle of an AC supply of peak value epsilon 0 is equal to epsilon 0 divided by over 2. This can be considered an important factor when dealing with AC power supplies and their applications. Today, we'll be discussing the fundamentals of AC power, more specifically, how it passes through pure resistor, inductor, and capacitor components. AC current is a dynamic, constantly alternating flow of energy, and each of the three components affects the power differently. With a resistor, the current is obstructed, causing it to drop in voltage. With an inductor, the current is slowed, causing it to store and then quickly release energy, and with a capacitor, the current is blocked, so it builds up until it is discharged. Understanding the dynamics of how AC current behaves in each of these components is essential in any electrical engineering application. It is important to understand the behavior of alternating current by studying phasors. A phasor is a vector with both magnitude and direction in the time domain. Alternating current and induced electromotive force vary sinusoidally with time at the same frequency, but may not be in phase. Therefore, we use phasor diagrams to represent them as vectors in a plane in order to simplify the study of such circuits. We take a look at the graphical representation of alternating currents and EMFs as vectors, also known as a phasor or Argand diagram, at slide 28. This diagram can help us calculate the electric field strength using this equation. E theta equals T sin T. The electric field strength is a function of time, as represented by the sin 2 pi ft term. When alternating current flows through a resistor with a resistance of R, the current, I, that it produces can be calculated as the instantaneous value of E, which is equal to E0, multiplied by the sine of angular frequency, T. Examining an alternating current, we can see that its voltage across the output of the AC source is constantly varying with time according to the equation equals 0 sin T or V equals V max sin T. Applying Ohm's law, the current I is also constantly varying with time as I equals I max sin T. Through understanding the alternating current and how it fluctuates, we can utilize it in multiple applications. Discussing alternating current, we can observe from the two equations that both the voltage and current are in the same phase, with no phase difference between them. This is an essential component in comprehending alternating current, and can be seen in the phasor diagram. An alternating voltage given by epsilon equals epsilon 0 sin omega t or V equals V0 sin omega t is applied to an inductor of inductance L, forming a purely inductive circuit. This applied voltage opposes the growth of current in the circuit, thus maintaining the current through the inductor. Comprehending the behavior of current in this type of circuit is essential for guaranteeing the security and precision of many electrical and electronic applications. The characteristic feature of alternating current is that the current lags behind the impressed EMF. This implies that the current is at its maximum when the impressed EMF is zero. Moreover, the EMF leads the current by 90 degrees or by pi(2 radians). To represent this relationship between the current and the impressed EMF in a AC circuit, the phasor diagram is used. Inductive reactance is the opposition offered to an inductor when current flows through it. This is represented by the formula XL equals omega L equals 2 pi FL, where F is the frequency of AC. It is measured in ohms, and its dimensional formula is mL2T3A2. The alternating current in a purely capacitive circuit flows in accordance with an alternating voltage. Equation 1 describes the voltage across the capacitor, which is V equals V0 sin omega t, with V0 being the peak voltage and omega t being the angular frequency of the current. Additionally, the charge on the capacitor is also fluctuating with this same frequency. By differentiating equation 1, with respect to the time, we can determine the rate of charge change on the capacitor. Alternating current, AC, is the expression for the instantaneous current through a capacitor, where the phase difference between the electromotive force, EMF, and the current is pi(2 radian or minus 90 degrees. This phase difference, represented by theta, is equal to omega t plus pi(2), where omega t is the angular frequency and pi(2) is the phase difference. Understanding AC provides a powerful tool in solving global energy issues. This slide talks about capacitive reactance, a measure of the opposition offered by a capacitor when current flows through it. It is also important to note that its units and dimensions are the same as that of resistance. Additionally, the RMS EMF is equal to the RMS current through the capacitor multiplied by the capacitive reactance. Finally, the unit and dimensional formula is mL2T3A2, which can be expressed in ohms. Electric current that reverses its direction periodically is known as alternating current. This can be depicted in multiple ways such as phasor diagrams, vector diagrams, and voltage, current waveforms, with each varying depending on the type of load in the circuit. If the present load in the circuit is a pure resistor, the diagram or waveform will be distinctive from a circuit with a capacitor or inductor load. These diagrams and waveforms for pure resistor, inductor, and capacitor can all be found in the slide. The current in an AC circuit containing only capacitance relates to the voltage in a specific way. It leads the voltage by 90 degrees, meaning the current peak occurs earlier than the voltage peak by 90 degrees, or 1/4 of a cycle. This is a very important concept to understand when working with AC circuits. When we connect an alternating current, AC, source across a resistor, it's important to understand the relationship between current and voltage. When current flows, it can lead the voltage, lag behind it, be in the same phase, or be out of phase. By studying these relationships we can gain insight into the behavior of AC sources.